Okay, hi everyone. Welcome to the January workshop. So today we'll be talking about the solutions to these bronze and silver January questions. And then, so as a general agenda, we're just going to be going over the 3 bronze questions and then the 3 silver questions. And then for the first 2 questions, teachers from the Competitive Programming Initiative are going to come in and teach. And then for the last question, we have a teacher from our sponsor, XCamp. So before we start, I'm just going to really quickly explain XCamp. So thank you so much for XCamp for sponsoring us. So XCamp is a Silicon Valley-based institute, and they offer coding classes for middle and high school students. So if you're interested in taking on advanced coding classes, or if you want to improve on USACO, I would definitely recommend going and checking out XCamp's classes. So their teacher will be explaining the last question for bronze, and then also the last question for silver. So we're going to wait a little bit for a couple more people to join, and then we'll get started. Okay, and then if you have any questions throughout the process, you can obviously type in chat, and then our teachers will go through and explain your questions and try and answer them. Okay, so let's look at the first bronze question hurdle.
Okay, my bad. Hi, my name is Amogha, and I'll be covering the first question of bronze, and that's hurdle. So first, we'll look at a summary of the problem, then I'll explain the method, and then finally we'll take a look at the code. So in summary, this problem discusses a parody of Wordle, which is like an actual game, and we are given 2 3x3 grids of uppercase letters. One is an answer grid, and the other is the guess grid. And we want to give out 2 numbers, the number of green cells and the number of yellow cells. So a cell in the guess grid is considered green if the letter in it is exactly the same as a letter in the corresponding cell in the answer grid. So if I have an A in row 1, column 2 of both grids, then that letter is going to be green. A cell is considered yellow if its letter is found in the answer grid, but not in the corresponding cell. The number of yellow cells is limited by the number of cells in the answer grid with that letter. For example, if there are 2 A's in the answer grid but 3 A's in the guess grid, where the 3 A's don't align with either of the answer grid's A's, only 2 A's count as yellow cells. So now let's take a look at the method. How would we solve this? So notice how the question does not mention any significance of the row or the column by itself, but only the specific position. So both row and column, and that's going to be unique for every cell. Because of this, we can treat each 3x3 grid as a string of length 9, where each character is uniquely positioned. So row 1, column 1 is always going to be the first position in the string, and so on and so forth. That makes sense. So first we will scan both strings, and if the same letter is found at a certain position, we increment the variable green. So that's one of the things we want to keep track of. So of course, we'll initialize a variable called green. And if they're the same in both the answer and the guess, then we want to increment that. Now, once we've done green, we can take a look at the yellow cells. According to the problem, if there are X cows of a certain breed in the guess grid and Y is less than X cows of this breed in the answer grid, then only Y if the X cows in the guess grid should be highlighted yellow. And obviously it follows that if Y is greater than or equal to X, where again, Y is in the answer grid and X is in the guess grid, we only mark X cells as yellow since that is all that has been guessed. So in summary, if Y is less than X, Y cells are marked yellow, and if Y is greater than or equal to X, X cells are marked yellow. It becomes clear that the number of cells marked yellow is the minimum of X and Y. So to track X and Y, we will use an array to keep track of letter counts in each string. And as we go across each letter, if both are non-zero, we know that this letter is found in both the answer and the guess, and therefore we can calculate yellow for that specific letter. So however, there is something we failed to take into consideration. A green square cannot be yellow, and that's obvious. So, and therefore that cannot be counted when looking at X and Y for the calculation of yellow cells. So we'll modify our green method from earlier. So what we'll have is an answer count array. And if you'll notice here, answer I minus 65, this is just going to convert the ASCII value of the capital case letter into an index that we can easily do. So we will take the answer count for that character and we'll subtract it by 1, and the same in the guess. Because once a cell is green, it cannot be yellow. So now let's take a look at the code in C++, Java, and Python. All right, so first we'll look at C++. So here we have our method. And so first what we'll do is we'll initialize our answer vector and our guess vector. And this just keeps it easier to track of for as we read in each string. And so what we'll do is we'll read in our strings, and then we have each letter. And right here we have int index. And so this is going to be the character minus the ASCII of A. So if you had the letter A, you would get 65 minus 65, and that would go into index 0. And that's when we would push back into this strings vector here. So we'll do this for the answer, and then we'll do this for the guess. And now we'll take a look at green. So remember in here, we have occurrences of each character, and here we're updating the answer and the guess string. So as you can see, for each answer and for each guess, if this specific character, J of that answer I, if they match between guess and answer, then we're going to increment green. So if a cell is green, it cannot be yellow, so it is also taken out of consideration. And that's what we use these count arrays for. All right. And then we'll have the yellow method, and this updates yellow based on the minimum number of character occurrences. And we don't need to update answer count and guess count because each letter is unique, and thus it doesn't need to be revisited. So because it's not just any kind of breed and there are only 26, you might as well just check all 26. So we have I equals 0 up to 26. And if these both are non-zero, then we'll just increment yellow by the minimum between these two counts. And then we can simply print out green and yellow. And as you can see, as we have here, we have A, B, B, B. So you guys see this test case here. And so we have, I believe, A in these two are going to be marked green. And then this C is going to be marked green. So that's 3. And then we have a B in the wrong spot. And then we have another A in the wrong spot. So that's going to be 2 yellow, as you can see. Taking a look at Java, we have something similar. This time we actually keep strings, 2 strings, answer and guess. And so we initialize answer count of size 26, 1 for each letter, and guess count as well. We read in all 3 strings, as we can just put them back to back. And same thing for guess. And then we update the occurrences of each character. At each index, we just increment if by subtracting 65 from the character itself. Then we take a look at green and yellow. If a cell is green, it cannot be yellow, so it's taken out of consideration, almost identical to the C++ code. And the same thing goes here for yellow as well. Then we simply print out green and yellow. And as you can see, this will run too. Finally, we have the Python code. We'll initialize our answer and guess arrays. And then we'll first read in these first 3 strings, which contain the input. Then we'll do the guess. We'll read in those 3. And then we have occurrences for answer and guess. And this is going to be of size 26. Then we update the occurrences, if of course, by doing the ASCII value trick again, by subtracting 65. Then we keep track of green and yellow. We do the same thing for the greens, same thing for the yellow as before in C++ and Java codes. And then we can print out green and yellow. And as you can see, this will run as well. And that's it. Without further ado, we'll let the next instructor present.
Okay. Let me just share my screen really quickly. Okay, so today I'll be explaining non-transitive dice from bronze problem 2 from the 2022 January contest. So we have like up to 10 test cases. And then for each test case, we're given 2 dice and they're both four-sided. So these first 4 numbers represent the first dice, and like the second 4 represent the second dice. So basically, we'll call dice A beating dice B if dice A has a higher chance of landing a higher number than dice B. So, and then we're tasked with finding a third 4-sided dice in which like none of the 3 dice beat the other 2. So each of the dice lose to one and then win to another. So they are non-transitive. So yeah, I'll be going over the solution now. Okay, so wait, so you can search all of the possible dice because yeah, so like before we go into like whether there's a 1 in time, the code to like check this is pretty simple. So here I have a wins function and I'll go into talking about that more later, but let's just call wins if dice A has a higher chance of beating, has like a higher chance of winning against dice B, and same thing here. So obviously if this is true, then the answer is yes, otherwise it's no. So why can we brute force all dice combinations? So the number of permutations with repetitions is n to a, where n is the number of distinct elements and is like the size of each group. Oops. So in this case, we have 10 distinct elements since the dice's numbers can only go up to 10, and then each sample has 4. Okay. And also, let me just answer this quick question in chat. So is it taken for granted that A beats B? Yeah, okay. So it's not guaranteed that the first dice is A and the second dice is B. So this doesn't, yeah, so this doesn't actually cover like directly what the sample case is, but we'll go over how to just have to check this in a second. Okay. Yeah, hopefully that answers. Yeah, so to find C, we're just going to brute force all dice combinations because there's only 10,000 possible dice combinations to search through. Okay, and now we're gonna go do like the wins function. So each dice only has 4 sides, so you can just like check every possible pair of drawing that there could be, and this will run in O n squared time, where n is the number of sides on the dice. So here we're going to keep track of a wins counter for A and a wins counter for B. And for each like pair of dice that could happen, if side A beats side B, then A will win. Otherwise, B will win. And then if A beats B, then the number of times that A wins has to be greater than B. So we're just going to return this. Yeah, the dice C only has 4 sides. Okay, and then I'm going to go over the code before. I'm going to go over the code before I talk about the time complexity. So if you guys want to look at the code as well, you can just click the link in chat. So this is a link to IDE.USACO guide. So you can just click on any of the tabs to view code in your language. I don't actually have Java code, but the syntax should be really similar to C++. Okay, so first we're going to generate all of our like sequences for dice C. So the way we can do this is through a recursive function or a function that calls itself over and over again. So yeah, you loop over all possibilities. So basically, we're going to create them and we're going to represent all the different dices as a list of 4 elements. So every time we haven't built a complete dice yet, we're going to iterate through all of like the possible numbers we could put on there, put that one in, continue building from that point onwards, and then like remove that element. So yeah, so we can determine if a die is more likely to be another die by just looping over all pairs of like numbers that they could roll. And then whichever has like more wins than the others will win the game. So that is this beats function here. Okay. And I'm just going to show like what this recursive function does because it's kind of like hard to see. So essentially, like we start out with an empty list. And then at this point, there's 10 possible routes we could take because we could start with 1, we could have a 2, we could have a 3, and like so on up until 10. And then for the second element, like the same thing, we could have up to 10 different combinations up to here. So this will go out into 10 directions, and then the same thing onwards until it reaches 4. So every time we reach like 4, that means that we've completed a 4-sided die. And now that's like a possible permutation. So I'm going to push it back into this permutations vector, which just like stores all of like the permutations that we made. Okay. Yeah, let me just share this instead. Okay. So that's what this put does. So I'm just going to over the input now. So we're going to read in all the test cases, and for each of them, we're going to solve. So we're going to define like die 1 and die 2 are basically going to be dice A and dice B. So this just reads in the input. And then here is the case where A doesn't necessarily beat B. So if dice A doesn't beat dice B, then we can just swap them, because if dice A doesn't beat dice B, then like dice B obviously has to beat dice A. So if we swap this, then this guarantees that this will like follow like the paradigm shown in the example, where A beats B, B beats C, and C beats A. And now for all of our dice in the permutation, if dice 2 beats dice 3, or dice B beats dice C, and dice C beats dice A, or this clause, then this is a non-transitive set of dice. So you can just print out yes and return. Otherwise, we print out no. Yeah. And also the reason we don't have to check if dice A beats dice B is because we already checked it here. Yeah. Okay. Does anybody, wait, let me just go with the time complexity first. So the time complexity of each case is always constant because every time we always generate all of the possible permutations and then check it for like every single one. So it doesn't execute more or less operations for all different values of dice sides. Yeah, so does anybody have any questions? Yeah. So Dustin just like dropped in a useful point. So there's only 16 possibilities that they're equally likely to occur. Yeah, so for this one, this prints out yes, no, no, which is the same sample here. 10 to the 4th, no. Yeah, so there's 10,000 combinations of dice. Yeah. Okay, so now I'm gonna show the Python code. So it's same thing, but it's just like different syntax. So we're going to build our sequences, but instead of using a vector, we're using a list, which is essentially the same thing because they're both dynamic arrays. And then we're just going to do the exact same thing for every test case. So we're going to die 1 and die 2, swap them if they don't beat each other, and then like just iterate through all possible dice 3. All of this is like the identical logic for the C++. So yeah. Does anybody have any questions? Okay. If not, I'm going to give it to the next instructor, which I think is Xieting.
Yeah, hello. I am Chou from X Camp, and I will share my solution about the third problem in bronze. Let me first share my screen. Okay. So the third problem is jout. The problem gives you a sequence hi and all of the hi is less than 10 to 9. And the length of the sequence is n. N is less than 10 to 5. And every time you could choose an I where I is less than n minus 1 and hi and hi plus 1 is both greater than 0. And then you could decrease hn and hi plus 1 by 1. Things you need to do is to output the minimum number of operations to make all the elements of h to be the same, or you output -1 if it is impossible. And that's a problem. And now let's come to the solution. First, let's take a look at the operation. Let's first do some analysis on it. We found that the I and I plus 1 always has the different parity. I mean that so every time if we decrease h1 and hi plus 1 by 1, we can now it is very natural to let us to focus on the two values, which is v1 and v2. We define v1 is equals to h1 plus h3 plus h5 plus ... and v0 equals to h2 plus h4 plus h6 and plus ... I mean that every time we use one operation, we found out that v1 is decreased by 1, and also v0 is decreased by 1. So the difference maybe less. We could define this value as s. S is equals to v1 minus v0. The value of s will always be the same. Okay, so this is the first observation we have when we read the problem. Okay, then we could start our category discussions. First, let's see what if n is an odd number. Finally, we need to make all the elements of h to be the same. So at the beginning, it is h1, h2, h3, hn, and finally, we could get the h1 prime equals to h2 prime equals to h3 prime equals hn prime. We could define this value as h. So now we are talking about which is odd. Okay, so now let's take a look at the value s, where s is we have already said that s will not change. So now s is equals to v1 minus v0. Since n is odd, so v1 the sum of the v1, the value of v1 is n plus 1 over 2 times h. Since there are n plus 1 over 2 values and all of them are h, so this is v1. And then with minus v0. V0 is equals to n minus 1 over 2 times h. So just do some calculation. We found out that s is equals to h. I mean that since the value of s will not change, so we could calculate s at the beginning, and then we know the value of h. So we know the value of the odd element after the operation you do. So the only things we need to do now is to check whether we could reduce all the elements h1 into h1, h2, h3 into h. So that's not a hard part. Let me explain it to you. We could take hi into account from 1 to n. For I from 1 to n minus 1. We just calculate the number of operations we act on I and I plus 1 in order. So first, let's take a look at h1. We need to reduce h1 into h. So, and the only things only operations we could do to reduce h1 is we take the operation to act on the H1 and H2. So that means after it, after we operation H1 and reduce it to become H, we'll reduce H2 into H2 minus H1 minus H. We could define this value as H2 prime. Okay, and that's the first operation. And then we take a look at H2. Then for H2, we also need to reduce the H2 prime into H. So the things we need to do is, and also we could easily find out that the only operation we could do now is to do the operations act on H2 and H3. So the things we could do now is that we could let H3 equals to H3 minus H2 prime minus H. And we could also define this value as H3 prime. And then we will let H3 prime equals to H. We just kept on doing these operations. And so how do we check whether this is valid? That's also not hard. So the only thing we need to do is to make sure H1 is greater than or equals to H and H2 prime after the modification made, which is calculated from H1. We need to make sure that H2 prime is greater than H. Also, H3 prime is greater than H, and so on. And also, we know that we first decide from Hn minus 1 prime that we need to calculate Hn is equals to Hn minus Hn minus 1 prime minus H. Up to here, we need to stress out that this value has to be just exactly equals to H. So the last constraint will be Hn prime is equals to H. Okay, so just simulate this process, and we need to make sure that all these n constraints should be satisfied. And that's how we solve for n is odd. Finally, since there's only one possibility that to let the sequence satisfy our constraint, so the answer is easy to calculate. That answer is equals to the sum of all the H minus n times H, where H is also the same as minus n times S. Okay, that's the part for n is odd. And what if n is even? Let me first erase my handwriting. For n is even, we also first take a look at the value S. We found out that now S is equals to V1 minus V0, which is equals to n over 2 times H minus n over 2 times H, which is equals to 0. So that means that if finally it is possible to do sum of operation to let all the H to be the same, that means that the S should always be the 0. So the first thing is we need to do that if S is not equals to 0, then output -1. Okay, this is the first things we need to do. Maybe I should not clear it. Okay, and then the next observation we need to have is that if we could reduce all the value of the H, the area of H, to H3 to Hn, if we could reduce them to be all the value of H, then it is not hard for us to reduce all the value to H minus 1. I mean that we only need to take the operations on the 1, 2, on the 3, 4, on the 5, 6, and so on. If we take operation on these positions, we will find out that we reduce all the positions by 1. So if if answer, I mean, if we could reduce all the value to h, then we could also reduce all the value to h minus 1. So that's remind us of a classical algorithm, that binary search. So we only need to binary search the finally value from 0 to the minimum of h. We only need to search the value h from 0 to binary to the minimum of the h. We need to binary search this value. Okay, and after we binary search the value h, we found out that this problem is just the same as before, that in the odd part, ODD part. I mean, we only need to check whether we could reduce all the value of h1 to h2 to h3 to hn into the binary search value h. So we just use the same process as before, and just to check whether we could reduce all the value by h to h. Why do we need to binary search this? That's because we need to find the maximum of the h to make it be to a valid operation sequence. So after we binary search the maximum h, that this is valid, we only need to output the same as before. Answer is equals to sigma I from 1 to n hi minus n times h. Okay, so up to now we have already solved the situation for n is odd and n is even, and just combine them, we could get the fourth solution. And we could find out that the check process will take on times. And for odd, we only need to use 1 check, and for even, we only need to use log hi check. So the 4 time complexity will become n times log min h, which is fast enough to pass this problem. And up to now, are there any questions? Okay, and then I will share my code for this problem. First is a C++ version. I didn't give out the for code. I just give out the main part of it. First, let's take a look at the solve odd. This is part to solve for n is an odd number. V0 and V1 is calculated in the main program, and this is passed to the solve odd sub process. Okay, we first check if V1 is less than V0. If V1 is less than V0, that means that we have to reduce all the value into a negative number, which is impossible. So if V1 is less than V0, we just output -1, as we have already said. And also, if we cannot reduce the all the value to become V1 minus V0, then also we should output -1, which means this is impossible. The check process is that we check whether we can reduce all the hi to vol. Vol is parameters passed to the check functions. So we just do these two check to check whether this is impossible, and then we calculate the answer. Here V1 plus V0 is also the same as the sum of all the hi. And since we have to reduce all the value to V1 minus V0, so we just use these expressions to calculate the answer. And that's it. That would make sense for solve odd. And for solve even, just as before, I had said that if v1 is not equal to v0, this will obvious it is impossible. So we put -1 and return. And then we start our binary search. We just binary search the value of the value of h. We need to check with every time we set mid equals to the middle of L and R, and we check whether we could reduce L hi to mid. Yes, and this is just a template of the binary search. There's not too many things to say about it. Okay, so finally, let's take a look at the check functions. For check functions, we use a variable nh to means the value of h after the process. So we first set nh is equals to h1, and every time we need to modify nh into vol. So if nh is less than vol, that means that there's no possibility that we could reduce L value to vol. So we just return 0. And then we use the operation to act on I and I plus 1. So to reduce the value nh into the vol, so we just set delta equals to nh minus vol. And then we reset nh into hi plus 1 minus delta. And finally, we only need to check whether nh is equals to the vol. Here, now the nh is actually means the h prime, and the h prime has the definitions just above we have said. Okay, and that's the part of the check functions.
Okay.
Okay, and then this is part. This is code of the Python version. And the Python version, yes, it has almost the same process as the C++ code. They have the same logic engine. They just didn't in some grammar. They're almost the same. You could take a look at it. This is the check functions, and this is for n is odd, and this is for n is even. And okay. For n is even, why binary search and search for what? Okay. Okay. First, why we should use binary search? That's because first we have an observation that if we could reduce all the value of the hi to h, then we could of course reduce all the value to h minus 1. That's because we could use a naive operation sequence that's 1, 2, 3, 4, 5, 6, and so on. That means that we could imagine a sequence that check h1. Maybe I could write this. If we check 1, we could consider a sequence check 1. Check 0 means whether we could reduce all the value to 0. Maybe the answer will be true, because that's because we could reduce all the elements to 0. And then the check 1, the answer will also be true. And finally, check 2, maybe now it will be false, and so on. And maybe we could use T to represent Chou and F to represent F. Oh. And we found out that the sequence of check 0, check 1, check 3, check 4 will be T, 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 F. Since if we have the statement that if check I is equals to true, then check I minus 1 will also be true. Since this statement is always holds that the T and F will of course have a boundary to separate them. So that means that we could use the binary search to find out the separation, the boundary of the T and F. If we have already found out the maximum T, that means that we could reduce all the element to this value, and since this is a maximum, then we could use the least number of the operations. So that will help us to calculate the answer. So for your questions, we binary search the value h that we need to reduce all the hi into h. And okay, is it clear? And any other questions? Check K. Okay. Check H. To check H has the same process as when n is odd. Maybe we could refer to the code. First, the value is h1, h2, h3, and hn. We need to check whether h is a possible terminate value of this sequence. And first, we need to find out that in order to reduce h1 into h, we have to take h1 minus h number of operations on 1 and 2. That's because the operation on 1 and 2 is the only operations that could reduce h1. So we need to use this number of operations, and now h1 becomes h, and then h2 was become h2 minus h1 minus h, which is and let's denote this value to be h2 prime. Okay, now then let's take a look at the h2 at these positions, h2 prime and h. We found out that since we have already determined the number of the operations we act on 1 and 2, and now the only operations we could do to reduce the h2 prime to h is the operation on 2 to 3. And of course, we need to do h2 prime minus h numbers of operations on 2 and 3. So just the same as before, we successfully turned h2 prime into h, and now h3 was become h3 minus h2 prime minus h. And then we could successfully to make the h3 to h3 prime. Yes, we just do this process from 1 to n, and we need to check every time whether h2 hi prime is less than h. I don't think binary search is required knowledge in bronze. Yes, yes, maybe there are some ways that not use binary search, but I think that for this problem, binary search is quite nature process to solve this problem.
So are there any other questions for this problem? Feel free to unmute or type in chat.
Okay, and since there's no other questions, so maybe I will end my screen sharing.
Okay, so we've gone through the 3 bronze questions, and then what we're going to do next is go through these silver questions. So we have Ryan, Dustin, and Xiting again talking about the questions. We're going to start with question 1, searching for soulmates. So if you have any questions, make sure to type in chat at any point, and then if you have any questions about any of the questions we've already described, then feel free to type that in chat too. Okay, Ryan?
Okay, so right now we're gonna be going over silver problem 1, searching for soulmates. So we're given 2 integers up to 118, so pretty big numbers, and we have to find the minimum of operations to turn a into b, giving that like we can only multiply a by 2, divide a by 2, and only if it's even, or adding 1. Okay, so for the sample case, this first one would take 8 operations. So the optimal would be adding 1, dividing by 2, dividing by 2, and just adding it by 13. Okay, so one of the biggest observations of doing this problem is to like think backwards. So to get a to like its lowest amount, which is 1, it take log 2a operations. So if we want to do the same thing to b, then we can just take the inverse of those operations. If we want to get 1 to b, then we'll just multiply by 2 and then subtract 1 to get to b. So like with this logic, we can just store moves to get a to 1 and then b to 1. And since there's only log 2 a plus b elements to store, then this will fit comfortably under the memory limit. And afterwards, we can just take the minimum difference between the moves of A and B plus the moves to get A and B in that state. And the reason we can just like modify B like this is because when we have to take like the inverse of the operations to get A to that point, we're essentially just like doing the exact same operations. And afterwards, we can just take the minimum of this. And since log 2 118 is only about 60, this an O of n squared algorithm will 1 in time. And also, there's also a case where A is greater than B. In that case, like we have to divide by 2 until it becomes lower than B, because there's no other operation that like decreases it. So we always have to divide by 2 in the case where A is greater than B. Okay. And then how should we store the moves for A and B? We can just store them in a vector or like a dynamic way. So after we do this, like after we just like make like a while loop and like keep dividing by 2 until you get to 1, the steps to get to like a certain point in moves A is just going to be the index, because if we have like A at index 0 and then like 1 at index like log 2a, then it'd be like the number of moves to divide by 2 to get to that point. And then to check like whether we can like move these 2 elements like together by just adding by adding the difference between A and B, we'll just check if A is less than B, because if it's not, then we can't consider this pair because we can't directly increase A to B. And we'll just take the minimum of div 2j minus div 1i, which is just the difference between like the code A and B. And we'll add I and J, which are just the moves to like number of steps to get A to that point, and then the number of moves to get B to that point. And then yeah, so once again, I think I'm gonna go over the code link, the code before I talk about the time complexity. So there's the code, and then there's only C++ code, but the Java solutions should have very similar syntax to that. Okay, so this is just like reading it input and stuff. So first of all, we're gonna have this edge case where A is already equal to B. So in this case, we can just print 0 and like return, because we don't have to perform any moves. And then after that, div1 and div2 are going to perform just like we described. They're going to store the number of moves to get A to 1 and B to 1. So this is just going to like calculate all of like the different divisions. So while A is greater than 1, this means that it hasn't like bottomed out at 1 yet. If it's odd, which is like A modulo 2, so modulo 2 just like gives us the remainder after we divide A by 2. So if 3 was A, divided by 2 would give us like a remainder of 1. So this would be like an odd number. Otherwise, if it was any other even number, it'd have a 0 remainder. So this wouldn't execute. So basically this is if A is odd. So if it's odd, don't increase don't increase A. Otherwise, when you divide A, I'm just gonna add this move to a set. At the end, I'm gonna push back 1, because in the worst case, where we can't find any middle ground for A and B, we can just bring them both down to 1 and calculate it from there. And we're gonna do the exact same thing with B, except we're going to take the inverse of the addition, which is subtraction, and this will perform essentially the same thing. And lastly, we're going to like calculate the minimum answer. So we're going to iterate through all the possible moves. And if A is less than B, meaning that we can directly increment from A to B, don't just take the minimum of I plus J, and then div2 I minus div1 I, and I already explained it already. And then afterwards, we'll just output an answer. Yeah, so let me just copy paste the sample case. Yeah, so this is the correct sample output. Does normal BFS work? Okay, so normal BFS is going to be, I think, yeah, so normal BFS would only work for the first 4 test cases, but timeout for the rest, because the numbers can go up to 1E18. So you can't like do that. Yeah, so I'm gonna move on to the time complexity now. Okay, so the time complexity is gonna be log 2 A plus B, because yeah, at most log 2 A plus B moves to store. Yeah. Okay, so does anybody have any more questions? Okay, if you have any questions in the future, you can just put them in chat. But yeah, I'll hand it over to Dustin.
So the next problem is cow frisbee, which is silver number 2. So the problem statement says, so given a sequence of heights h, determine the distance between all unordered pairs LR that exists such that the maximum of all the cows in between L and R is smaller than the minimum of those 2 heights. So as the example, we have this input with heights 4, 3, 1, 2, 5, 6, 7, and then the total distance is 24. So if I just select one pair, for example 1, 5, we can see that 1 and 5 work because the minimum of 4 and 5 is 4, and then all the heights in between are less than that. So the first observation is that we can, to process this, we should sweep through the array, and at each index we should find the sum of distances for all valid pairs that have a right index at that element. So going back to our example here, so if we were at 5, for example, we would want to count the pairs 1, 5, 2, 5, and 4, 5. So with this solution, we have n squared, which is enough for the first subtask, which is 3 test cases. So we want to optimize this to O of n log n, or O of n. So the second observation we want to make is when we're looking backwards, what cows can we throw the frisbees to? So in this simple example, if we're at cow 5 and we're looking back to see which cows we can throw a frisbee to, we see that we can throw one to the cow of heights 2, 3, 4, and 6. So we make the definition that this is a valid set, and then so a valid set of an index is a set of cows you can throw a frisbee to. And the valid set is colored blue in this example, and the valid set is also ordered. So the ordered set would be 3, 4, 5, 7 in the order of the indices. So we have a couple of lemmas that'll help us solve this problem. So the first lemma says that if at least one cow with a height greater than or equal to the current cow exists that occurs before the current cow, then only the rightmost cow satisfying that criteria will belong to the valid set. So to make this more clear, I have the same example here, and we see that there's only one cow here, the cow with height 6, that belongs to the valid set that's higher than the current cow. So we have a cow of height 7 here, but notice that this doesn't belong to the valid set. And likewise, if you were to have any more, then none of those would belong. And the reason is because the minimum, and any cow that's taller than that has it doesn't really matter how high a cow is if it's taller than the current one, because the minimum of the other cow and the current one is always going to be the current cow. So then we can't throw a frisbee between cows 1 and 8 because this cow at 3 would be blocking it. And then there's sort of a formal proof to that here, but I'll just skip over that. So then we have a second lemma, which is that the valid set of any index forms a strictly decreasing sequence. So what this means is that if we were to consider all the cows that cow 8 could throw a frisbee to, their heights would be strictly decreasing. So we see that there's a 6 here, then everything else has to be below 6, and then 4 here, everything else has to be below 4, and so on. So this is why we can't sort of throw one to 4. So using these two observations, we can sort of derive our third hint, which is that there's at most 2 n valid pairs. So two things we want to consider is why is this true and how does this help us? So the first thing is why is this true? And the reason it's true is because if we consider some pair A and B, if we can sort of think that like if B is taller than A, then nothing else to the right of B can really receive a frisbee from A, because B will always block A in that way. And then if A is taller than B, we know that then it sort of doesn't matter, because by lemma 1 we know that there's at most one cow that satisfies this property. So there's at most one cow that's taller than each cow that's in its valid set, and then every cow is dominated by at most one other cow. So we know that there's at most 2n pairs. So with this observation, we can sort of enumerate all pairs and just compute the distances between them, which makes this problem a lot easier. So we're finally arriving at our solution. So for each cow, we can pre-compute an index p of I to be the index of the rightmost cow before I, such that the h of p of I is greater than hi, or -1 if it doesn't exist. So what this means is that for each cow, we would like to pre-compute the index of the last cow that has a height higher than the current cow. So we know that for an index I is not equal to 1, index I minus 1 must be in its valid set. So that is to say that every adjacent pair must be a valid like configuration. So we traverse the P array starting from I-1. So the valid set for I is I-1, and then we go to cow before I-1. That's P of I-1, and then P of I-1 until the height is greater than H of I. So recall that lemma 1 states that we can only have at most one cow that is greater than the current height, or it becomes -1, which is to say that cow of that height doesn't exist. So we can look at our example here. So if we start at 2, which is 8 minus 1, this cow of height 2, we go to the one before it, which is 3, and then we go to the one that's higher before it, which is this 4, and then if we go to the one higher before that, this would be 6, which is already higher than our current index, so we can just stop there. So the last we can just loop through all of these because there's only O of n of these. So the last step that we can use to calculate P of I is to use just to calculate P of I, and there's a lot of ways we can do it. We can do it using a segment tree, a linked list, a balanced binary search tree, but the method that was intended was to use a stack. And then this also gives a very convenient solution because the elements that we pop are also the elements that we need to process anyways. So just hopping right into the implementation, the lines 4 through 12 are just input and initializing variables, and the main part of the code occurs here. So we loop through all of the indices from left to right, and then while the stack is not empty and the top of the stack is less than the current height, then we want to add its contribution because that's a valid pair, and we want to pop the top of the stack. And then if the stack is not empty, we would also like to add the contribution of the next highest cow, because by lemma 1 we always have such a cow. And then this is sort of an edge case, but it's fine if you sort of omit it. But if the current cow at the top of the stack is equal to the height of the current cow, then we also want to pop that. And then finally we just add the cow to the stack. So the stack will always be monotonically decreasing. And then at the end we just output the answer. So does anybody have any questions? If not, then I'll hand it to the next instructor.
So before we continue, remember the recording for this is going to be posted on the CPI channel later. So if you missed any part of the workshop or you want to review anything, then it's going to be on the YouTube channel. So this is going to be the last question, silver question 3.
Okay. Hello, everyone. I am Chou from Chou, and I will tell you my solution about the third problem in Silver Career 2. The problem there are n cows and m career. Both nm is less than the 25, and each cow has a favorite career and a second favorite career, and she will take the career by this priority. What you need to do is to find a permutation so that maximum the number of cows who eat her career. You need to output one of the optimum permutation. Here, I said that the cow would take the career by this priority means that, in fact, all of the m career, there are only one unit. There are only one unit of each career, and the cow would take the career in order. He would first check whether his favorite career is remain. If it is remain, he would choose his favorite career and just go away. And else, if his favorite career was eaten by the previous cow, he would take her second favorite career. And also, if he takes his second favorite career, he will also just eat his second favorite career and go away. And else, she would go away with empty stomach. So we need to do is to maximize the number of cows who eat her career. Okay, but this problem is an interesting problem. Maybe. Okay, I think the most interesting things we could do is to turn it into a directed graph. I mean, since every cow has two careers related to her, the first favorite, the favorite, and the second favorite, we could use a directed graph to represent it. I mean, all the career is now a vertex in the graph, and all the cow becomes a directed edge in the graph. We just, for example, for the first cow, her favorite is 2 and her second favorite is 1. We just link an edge from 2 to 1. This edge, this directed edge is the first cow, and we use this to represent the cow will first choose the second career and then choose the first career. And also, let me draw something more about this example. The second cow, he will choose first 3, then 4. And the third cow will choose first 2, then 3. And for the first cow, he will choose first 6, then 5. For the next cow, first 7, then 8. For the next cow, first 6, then 7. For the next cow, first 7, then 5. And for the last cow, first 5, then 8. Okay, and that's it. Then, using this diagram, it is easy for us to figure out the answer. Notice that there are of course 2 steps in the problem. That first we need to find out the maximal number, and then we need to construct the optimal permutation. Okay, first let's do the first part. How to calculate the maximal number. First, it is easy to figure out that for each connected component, we can solve them separately. So for each component, maybe for example, for the component 1, connected component 1, 2, 3, 4, let's do something about it. Let V be the number of the vertex. Also, number of the vertex. Also, maybe we could see that V is the number of the career in the graph, in this connected component. And also E is the number of the edge. Or we could see that E is the number of the cow in this component. Okay, so we could now state that the number of cow in this connected component that could eat the career is just equals to the minimum of V and E. And that's always could be possible. But that's because since there are only V, here V is just corresponds to career. And E is correspond to cow. Since one cow could only eat one career, so this of course is the upper bound of the main VE is of course the upper bound of the answer. And also, if we just, if we just define, take any order of the permutation, then this could always be reached. So now we know that the maximum number of the cow that could eat a career is just equals to minimum VE. I mean that for each component, maybe we could use CON as a component. For each component, here is the final answer is equals to, for each component, the minimum of the component dot V, I mean the vertex in this component and the edge in this component. Okay, up to here, we just find out the maximum number of cows that could eat a career. Okay, then what we need to do is to construct a permutation to reach this bound. And how to do this? I think up to now it is already an interesting problem, and after it, maybe the code will be a little bit difficult to implement. So how to do this? First, let's take a look at the. I need some space, maybe here. First, let's take a look at the condition that v is equals to e minus 1. Sorry, v is equals to e plus 1. Or maybe in the case that, for example, in the 1, 2, 3, 4. In this case, I mean that now, if we first ignore the direction of the edge and just regard this as an undirected edge, we could find out that we could find out that this situation is just a tree. This graph is just a tree. So for tree, it is easy to define. We just need to assign each. We just need to randomly choose a root. The root is not related. We just need to randomly choose a root and just use the edge in the DFS order. For example, if we choose 1 as the root, then we just do the DFS problem, and we got the sequence. First we visit this edge, and then we visit this edge, then we visit this edge. So we just need to output the 3 cows. The first cow is this, and the second cow is this, and third cow is this. No matter whether this cow want to eat, this cow is from the root to other points or in opponent directions, this doesn't matter, because we can see that no matter where the vertex is, the leaf of this vertex, I mean the vertex with the higher with deeper will always be empty, and the cow could always eat the second career. So for tree, if we just determine the permutations by the DFS order, all the cows in the trees, in another word, all the E cows in that trees will be have 1 career to each. So the situation for the tree is now finished. Okay, then what about the situation that is not a tree? Okay, for that is not a tree, for example, in this case, we know that if we take the DFS of the graph of an undirected graph, yes, also in these situations we also regard the edge as an undirected edge. So if we take a DFS to the graph that is not a tree, then of course there will some loop. So maybe, for example, we take a look at this loop. Okay, so what could we do to why we need to find out a loop? That's because for the loop we need some special process. We need to we need to do something to let these 3 vertices could be eaten by these 3 cows, the first cows, the second cows, and the third cows. We should make sure that these 3 cows could definitely eat these 3 vertices or these 3 careers. And after this, we just need to assign each career a cows, and this could reach the bound of the main connected component, the number of the vertex and number of the edge. So we only need to find out a way to assign each career to one of these cows. How do we do this? This is not a hard part. We just need to maybe, for example, this is a loop of the. This is an arbitrary loop. We just need to first think about take any edge as the first edge. If this edge is from the vertex x to vertex y. We just check whether this, okay, I mean that if this edge is from vertex x to vertex y, then that means if we first let this cow, maybe cow 1, maybe we let this cow 1 as first, then he will definitely take the career x or vertex x. Then we just assign the permutation as C1, C2, C3, C4 in this order. I mean, in the counterclockwise order. By this way, we will find out that the C2 will definitely take this career because no matter what is her prefer, because the career X is already taken by the first cow, then the second cow will definitely take this career. And also for the third cow, this cow will definitely take this career. And for C4, he will definitely take this career. And also in another condition, if the C1, maybe I could use blue. If C1 is in this direction, then that means that the first cow will definitely take this career. Then we just rotate the order. I mean, we just use the permutation C1, C4, C3, and C2, and then we let the permutation to let the other cows to be in a clockwise order. Also, the same process. If we then let C4 to decide which cow he would eat, then she would definitely eat this career, and also this career and this career. So by this way, we could successfully in letting these some cows to eat these all of these careers, and then we could now draw the graph in this way that there is already a loop. Then for other vertex, we just find out any spanning trees. We just need to find any spanning trees of other cows and other careers for this subgraph, and we just as same as the tree situation, we use the permutation in using the DFS order, that we first let this cow to decide, and then let this cow and this cow and this cow. Of course, there may be some other edges. Maybe there is an edges that like this, but in fact, this should not be taken into account because we have already reached the upper bound of minimum of V and E, since we have already assigned each vertex a cow to each them. So that means that we have reached the upper bound, and this is the best answer we could reach. So that will be optimal permutation. That will be optimal construction. Okay, and then we could go to the code. The code is a little bit long because finding loop and doing this DFS is a little bit long to implement. This is the main part. We just first read the graph, and then we process all the connected components one by one. If we visit one component, we just set the visit I to be 1, and else we just expand I. I mean, expand I means solve for the component with I. And after it, we just set, okay, and this is part of the print the answer. That's not very important. So what is expand? For expand, we just first find whether there is a loop in the start in this component. If there is no loop, that means we just print that's not I mean this is a tree structures, so we just return else. We for all the loop and we set their visit and we use DFS to get the answer, to construct the answer. And what is DFS? DFS is very important, very simple. That we just visit, we just do this, and we never visit vertex that is already set by the visit 2. So we only visit the vertex that is visit 2 is equals to 0, and we just visit it, and we first push back this edge, or we first set this count into the answer, and then we go to the deeper vertex. That's it. Okay, and finally is find loop functions. The find loop functions, yes, it is just the finding loop using the DFS. Yes, what we do is to use visit 1 to mark all the vertex we have already visited, and every time if we go back and find the vertex that we have already visited, we just break the pop the stack and get a loop here. If we find some vertex that is already visited, we just pop the stack, and get a loop, and also maintain the answer. Yes, and we return. And also we just do the normal DFS part. Okay, and that's it. That's the final slides. After we find the loop, we could successfully construct the answer. And after we construct the answer, we just need to print it out, and that's all. Any questions? Anyone have questions on this problem? Someone asked me that what is the second value of the pair of the edge? Oh, this is just a implement technique. I mean that for all the edge I, we set if there is an edge from x and y, we just set the edge from x to y has the label I times 2 plus 1. No, this has the level I times 2. And also we link a virtual edge from y to x has the level I times 2 plus 1. This is because this level was very useful, because if we have an edge has the level e, then e over 2 takes the floor. The floor e over 2 is just the ID of the edge. And also we could use the value e module 2. By this value, if e module 2 is 1, then we could tell if e module 2 is 1, we could tell that this edge is how do I see? This edge is not the actual edge. This is a virtual edge. I mean, this is the edge from y to x. And also, if e module 2 is 0, then that means that this edge is the actual edge. And any other questions? Someone asked me that. Okay, and now we are talking about the problem of the career. That is the third problem of the silver contest. I think that the main idea of solving this problem is that we could first diagram this original problem into a graph, a directed graph, and that could help you to think more about this problem. This could help you be clearly about this problem, and then we could easily find out the upper bound. To solve this construct problem, a more popular way to do this is to first find upper bound, and then try to construct a solution that could reach the upper bound. If we could not reach the upper bound, we just try to figure out why we could not reach the upper bound and reduce the upper bound. Else, if we finally successfully reach the upper bound, we could then that's all. We get the answer, and that's it. In this two way, maybe we could write the third that reduce the upper bound. We just repeat doing the third process and the second process. And I mean, we just 1, 2, 3, 2, 3, 2, 3. We just kept on doing this process. And finally, we found out that one time the upper bound, and we successfully reach it. And then we finally finish this problem. And that's it. Okay, and any other questions? And also, I think you could ask questions on the previous problem. I think they are also willing to answer you. So maybe I think I could first. Oh, how did you think of using graph for this problem? Actually, I think that graph is not the necessary step to solve this problem. That's just because using graph, we could have a better look at the structure of this problem. This is just for plotting. This is just for, you know, that if we just take a look at this set of data set, it is quite, we just didn't know what this would happen. But if we just plot it into a graph, then it is easy for us to find out, to help us think about this problem. I think that the reason maybe is that the first career and the second career is just related with an age, and that's it, I think. Also, I think I'm sure that if you didn't use the graph, you could also come up with the solutions, maybe even have the same code as me.
Okay, are there any more questions? Feel free to type in the chat to everyone. Okay, if not, then we'll be ending the workshop here. Thank you so much for coming. Before we end, we have a couple words from our sponsor, XCamp. So obviously Siting is from XCamp and he's come up with amazing solutions. So if you want to go through high level or advanced questions, or for example, classes, then I would definitely recommend XCamp. So does XCamp want to speak real quick? And then again, the recording will be posted on YouTube. So the Competitive Programming Initiative YouTube channel, I'll post the recording with the full workshop.
I think that maybe Yuan Xu want to talk about something. So please wait for 1 or 2 minutes.
Oh, hi, actually I'm here. So Melody, can I talk just for 1 to 2 more minutes?
Yeah, go ahead.
Yeah, cool. Yeah, so my name is Yuan and I'm the co-founder of XCamp, and also I'm the teaching side. I'm in charge of the teaching side as well. So in general, XCamp is a competitive programming institute in Silicon Valley, and we also provide online class as well. And it's a great opportunity to be here, and I'm really happy to have XCamp in partnership with CPI, and all together going forward, we will have more events, and hopefully we will host such kind of teaching tutorial sections for every single USACO and test going forward. And we are hoping that we are able to provide more and more valuable takeaways for all the competitive programming enthusiasts. And I do have 3 things I want to share. The first one is that we do have an introduction video. Let me do a quick screen share so that everyone can take a quick look.
Computer science and artificial intelligence are tools that will change the future. XCamp Academy is a community dedicated to inspiring and cultivating the next generation of computer science and artificial intelligence talent. XCamp Academy was founded in August 2017 in Silicon Valley by 2 Google software engineers. The name XCamp was inspired by the variable X, which represents unlimited opportunities. XCamp's curriculum is developed by Mr. Xianyou Xu, a Chinese diamond-level international gold medal coach. Our staff here in the US is composed of senior software engineers from major technology companies in Silicon Valley. In addition, we have strong support from international and domestic competition winners. From beginner-level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. We prioritize personalized education, with problem sets tailored to each student's needs and an enrollment system that encourages grade skipping. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of now, more than 80 XCamp students have qualified for the USACO Silver Division and above, including 13 who are in the Platinum Division and 33 in Gold. During the Teams Code Summer Virtual Contest, XCamp's teams won second prize in the Intermediate Division and first place in the Advanced Division. At the 2021 Harker Programming Invitational, our students won first and second place in the Advanced group, and the top 3 teams in the Novice group were all from XCamp. Here at XCamp, we believe that students have unlimited potential and can change the world through coding.
Okay, so let me stop the screen share. And yeah, we provide for beginning level class up to competitive programming for USACO as well, and all the way to the students who want to shoot for camp. And we're more than happy to help you and to find out where's the gap and how to improve as well. Lucas Zheng asked a question: what makes XCamp special compared to all the other options at, for example, like StarLeague or AlphaStar? I think I don't have a very clear idea of how, I mean, like a clear idea of how they run their program, but basically I can talk about XCamp. So the way we do it is that we take USACO as a side product, and we mainly want to develop your knowledge and build your knowledge to be complete, so that you have really solid foundation in algorithm and data structure in general. And if you have more commitment and have more energy, we will push you to do the competitive programming. And a very special thing about us is that we take USACO not as the eventual goal, as a side product. And in the same time, we provide very complete tutoring and coaching, starting from the beginning level all the way to the highest level of class. So for example, right now we have close to 20 Platinum students, and we also divide them into 2 different groups. And one of them takes 2 mock tests every single week. And they really do really intensive training, and they are shooting for camp. So we do this kind of a very special program for them, and it's very customized. And we have a very strong tutoring and coaching from strongest past competitive programming players. Yeah, and some of the teacher are IOI #1. Not Benjamin Qi, but yeah, we do have some students because XCamp collaborates with Xinyu, which is the Chinese school, and that school has several IOI world winner #1, 2014 and 2016, Jingce and Xinjiang. Yeah, I think that's really distinguish XCamp with other institutes. I think yeah, that's it. And also we also provide the fundamental class as well. Yeah, if you're interested, feel free to go to our website. Yeah. I think I do have one more thing to share, since you asked about the class. So one thing I want to share is give me one moment, is the code, or say contact information that you can find us. Okay, so I'll keep this page for some time. Feel free to take a screenshot or something like that. Please note that we do provide the discount code for all the CPI members. And please take a screenshot, and later feel free to contact us as well. Yeah, I'm here to take more questions, but I'll leave this page for now, probably for 1 more minute. In the same time, we do have one more event. That is our colleague, because we are from Google. So we periodically organize some events related to AI, related to programming and engineering in general. And we do have a colleague who is specialized in artificial intelligence, and he will talk about I think it's the AI to power the Super Mario as a gaming. Yeah, basically, I think it's super fun, and as myself, I'm not really looking forward to that event as well. So do go to our website and get more information about it as well. Okay, so if you want less more information, or maybe you want to take a screenshot but couldn't have the opportunity, then feel free to email us at info@xcamp.org. We will keep in touch. Yeah, I think that's all for me. Thank you so much, and we are really looking forward to the next event. Thank you.
And thank you to XCamp, and thank you for everyone for coming and staying for the workshop. So that's the end of the workshop. We'll post the recording. Thank you all so much for coming, and have a good night.